was speaking. How would you like to stay just as young as you are, not to grow a day older for the next 200 years?
Girls, just imagine what that means.
This is news, Albert. Big news.
Throughout time, we mortals have gone to remarkable lengths, trying to stop the aging process, seeking to delay death, if not avoid it altogether. Now, as astonishing as it may seem, science has uncovered a key to endless youth. An elixir of life itself. Discovered deep within the cells of a tiny pond creature. Far from fiction, in 2009, its discovery won this Australian-born scientist a Nobel Prize. She hadn't been seeking immortality at all.
It was just this wish to get at the bottom of how life works.
This is not just going to cure aging, it's going to literally change the world.
This is something that has huge impact on something that matters to almost everyone, which is how long we live, as well as how well we live.
But there's a challenge. For this remarkable substance has a paradox at its core. It offers endless life, but it can also kill. This riddle of cellular immortality is shaping all our lives. From how well we age to how long we may live. Most of us think of aging in terms of chronology or time. 1,000 years ago, we could expect to live for around 30 years. 100 years ago, 50 was the average, at least in developed countries. Today, we can expect to live Take Ray Newsom. He may look like an average 16-year-old, but inside his body, his cells resemble those of an extremely old man.
I have a 16-year-old body, but I could have 85-year-old lungs or whatever. My organs are going at a faster pace than I am.
Deep in his cells are signs that he's aging at a devastating rate.
He's got the breathing issues. He can't breathe. He's very slow moving. His memory, he'll tell you, his memory's not there. The morbidity age for severe cases is 16, and Ray will be 17 in January.
Paulette Salt also has signs of premature aging, but in her case, it appears to be linked to stress.
I feel older. My body feels more aches, more pains. I'm tired more often.
In contrast, Jack McClure's cells appear to have slowed their aging process.
I'm aging 30% less rapidly. And I now have a different expectation about how long I'll live than I did before.
And at 92, Dal Richards defies our expectations. He has no signs of any age-related disease.
A health-wise, I don't have to pay attention to it. I just, and I don't.
For the first time in history, we are beginning to understand why some of us age faster or slower than others, and what we can do to influence it. Exactly why we age has long been a mystery, one that's been partially solved by aging expert Professor Leonard Hayflick.
If you look at automobiles of a particular year and a particular model, you will find that not all cars of the same make, model, and year age at the same rate. Some will require repairs rather early on, and others will last amazingly long without repair. That's because of the differences in wear and tear, if you will, in construction materials, perhaps workmanship varied a little bit. That's the same thing, analogously, that happens in biological material and in humans in particular.
50 years ago, Len peered into the human vehicle and discovered our cells have a limit to their lifespan. Our bodies are made up of around 100 trillion cells, and most replicate by dividing over and over again. Some reproduce or double over days. Others can take years. Before the 1960s, scientists believed that if we only knew how to keep cells healthy, they could live forever, that our cells were, potentially, immortal. But Len Hayflick showed that certain human cells only replicate around 50 times. Then they stop. They enter a cell's version of old age, called senescence, where they can't reproduce, and eventually they die. But when Len put cells in the freezer, he discovered something remarkable.
They have a memory. They remember at what population doubling level they were when you put them into the freezer, and when you reconstitute them, they take off from that point to go through the remaining number of doublings that will then equal 50. If you froze them at 40, they have 10 left. If you froze them at 10, they have 40 left, etc.
Len argued there must be a mechanism inside the cells, counting down with each replication, until they reached their limit, the so-called Hayflick limit. So something must signal cells when they reach the end of the line. Something tells them how long they have to live. But what? As a young girl living in Tasmania, Australia, Elizabeth Blackburn had a love of difficult questions.
When I grew up here in Tasmania, I was surrounded by nature and surrounded by animals and plants and trees. And I just wanted to know, how does life work?
This would lead her into molecular biology, where she would ask, what lies at the ends of our DNA?
The ends of DNA is like a biological wilderness. People knew about the genetic code when I was starting my research on DNA, but they just knew nothing about what goes on at the ends of DNA molecules. And so it was just this wonderful mystery. You know, some people like to look at what goes on at the ends of galaxies. You know, it was just an exploration. What's there? And so I kind of like those lonely places.
Little did she realize she would uncover a vital secret deep within the cell. Inside a human cell is the nucleus. Inside the nucleus are 23 pairs of chromosomes. These are long threads of DNA carrying the genetic information. Right at the ends of the chromosomes are special stretches of DNA called telomeres. They are known to play a crucial role protecting the ends of DNA.
So we kind of think of this like the tip at the end of the shoelace, because if you don't have that tip, then the end of your shoelace frays away very quickly. You know, your shoelace won't work properly if it doesn't have a tip. And it's like the end of a chromosome, the end of a DNA. If it doesn't have an intact tip on it, the telomere, it too will fray away.
When a cell is replicating, it can't copy its DNA all the way to the end. And so, telomeres shorten with each replication. If telomeres get critically short, the cell can malfunction and die.
If you don't have caps on the end of a chromosome, then the ends become very sticky. It's almost like the shoelace ends become tied together. And this messes up the genetic material. This can have disastrous consequences for cells. A little bit like if your ends of your shoelaces are tied together, you're going to trip up and fall.
Liz studied tiny, single-celled creatures found in ponds called tetrahymena. They have enormous numbers of small chromosomes. She carefully determined the structure and makeup of their telomeres. Then she noticed something odd.
Something puzzling was happening at the ends of the DNA, the very short chromosomes in tetrahymena, and that was that DNA was getting added on to the ends of these chromosomes, and this was not anything that anybody expected DNA to do.
Something was adding new DNA to the ends of the chromosomes. The telomeres were not wearing down. And so the cells could replicate endlessly. They were, in effect, immortal.
We started to think there must be some new process that nobody had ever heard of before. It wasn't in the textbooks, and it wasn't anything that people had described before for DNA, and yet it had to be something to explain what it was we kept on seeing. And so I wanted to hunt this down.
For centuries, alchemists hunted a magical substance, an elixir of youth, made from the legendary Philosopher's Stone. This stone was believed to impart immortality. For the ancient alchemists, it was all about revealing and reinterpreting the basic materials of life. For Liz, it was the beginning of a long process, hunting a phantom-like substance. The journey started in 1975. By the early 80s, she was based in San Francisco, and together with geneticist Jack Szostak, saw that telomere lengthening was happening across different species. Something big was going on. Then in 1984, graduate student Carol Greider joined the hunt.
Clearly, there was evidence that something must be elongating telomeres. And so we were just very curious as to how that could happen. What would be the way that the chromosomes would be elongated to balance the shortening that should occur every time the cells divide?
For 9 months, she laid bait for the substance, designing experiments, trying to make it show its molecular face. The big break came on Christmas Day, 1984.
I went in on Christmas Day because I was just curious what had happened in that experiment that I had done the last time. And that's when it was really quite startling, because the result that I saw on this X-ray film was clearly this 6-base repeating ladder, which was exactly what you would predict. And so it was a very visual, wow, there's something going on here. What I had been looking for, but really in spades. So that was just really exciting.
They had found an enzyme, a chemical catalyst that could keep telomeres long and keep cells reproducing forever. They called it telomerase. It would have profound and unforeseen implications.
We were just trying to understand how it is that chromosome ends can be maintained through each round of cell division. So there was no thought about human diseases, cellular senescence, cancer, degenerative diseases. All of those came later. So it was really curiosity-driven science, but we did know that understanding something very fundamental in the cell, like how a chromosome replicates, would have important implications, but we just didn't know what those implications might be.
We wanted to understand life, and we wanted to see, is this really a process happening at the ends of chromosomes which nobody has ever seen before, or what? It was just this wish to get at the bottom of how life works.
They had unknowingly uncovered the secret to endless life in cells. Now the question was, could it work in people?
Almost all of us wish we were just a little younger than we are. Ladies quite late in their 70s can be heard addressing each other as girls. Very rich old ladies, even rich old gents, have squandered fortunes on monkey glands and I don't know what all, in the wistful hope of turning the clock back or at least slowing it up a bit.
I can't imagine you with gray hair.
Alan, I couldn't bear to see you get old and ugly.
Like
It's going to affect every disease practically we've ever heard of. I think this is going to be the biggest thing that ever hit the planet when we actually find a drug that turns on telomerase. It's going to literally change the world.
I've never enjoyed anything as much as I have as turning over a rock for the first time and finding one of the mysteries of life and seeing it for the first time with my own eyes.
cell biologist Dr. Calvin Harley, together with Carol Greider, was the first to link the length of our DNA caps, our telomeres, to human aging.
And here's Jesse's famous cat.
In the 1990s, they tested a range of people, including Cal's own family, from his father down the generations to his then young children. They discovered that generally, the older the human, the shorter the telomeres.
All right, Andy?
So Thanksgiving and telomere biology.
It was a revolutionary idea that we could see the aging process in the DNA of a human being.
It's almost like a fuse, and you get to a point where you have critical telomere loss that actually triggers genetic instability. And it basically is a genetic time bomb in the sense that the cells don't quite literally explode, but they can implode or basically die.
When our telomeres reach a critical length, our cells reach the end of the line. And as our cells age, we age. The challenge was to see if it could be stopped. One of the first to embrace the challenge was biologist Dr. Michael West.
When we started this work maybe 15, 20 years ago, we knew that the aging of cells had something to do with the aging of people. You know, the graying of our hair, the wrinkling of our skin. In my opinion, today, the data would suggest that upwards of 80% of human aging is caused by the aging of cells. And of course, we now have the key to rewind that clock of cellular aging.
The enzyme telomerase was that key. Mike raised $40 million to build a biotech company called Geron, from the Greek for old man. They won the race to discover a human telomerase gene. And suddenly, the immortalizing enzyme could be activated. They put it to the test in none other than the cells of Leonard Hayflick, the man who, in a way, started it all.
And so Dr. Hayflick's cells were the first cells in which we introduced telomerase to see, could we reset the Hayflick limit, the true Hayflick limit, the proliferative lifespan of Dr. Hayflick's cells. I remember I called the experiment in my notebook the immortalization of Dr. Hayflick.
The cells on the left are examples of healthy young cells. The ones in the center are older cells, nearing the end of their reproductive life. And on the right are the same cells after adding an extra gene for telomerase. They had become young again. And they were replicating over and over.
And of course, the excitement was when the cells with telomerase started to break through and kept going while his cells without telomerase started to age. And that, of course, that was a breathtaking time, really. Staggering in its implications, I think.
Appropriately, it could have been called the cellular fountain of youth, because we really did immortalize cells and give them essentially an indefinite replicative capacity, not as old cells, but we could actually turn back the clock, increase telomere length, and have cells live 10 or 100 times longer than normal, but in a youthful state.
But so far, this gene therapy approach only works in cells in a petri dish.
If we had a way to take this discovery in the telomerase gene and activate it in the human body and use it to reset telomeres in an aged person, and then I think importantly turn it back off, then I think we would actually see an extension of human lifespan, a retardation, a slowing of the onset of age-related degenerative diseases. Unfortunately, we don't know exactly how to do that today.
So Geron went looking for another way to activate telomerase, testing plants used in traditional medicine. One molecule, TA65, was found in a Chinese herb. Self-made millionaire Noel Patton took a license from Geron to sell TA65 as a dietary supplement at a cost of around $15,000 a year.
I was just blown away with the idea that there was a way to make a cell live forever. The first thing I thought, this can't really be true. And then as I got into the biology, I found that it is true, and it's now scientifically accepted by everyone that you can make cells live forever. As a businessman, the sky is the limit here.
Dr. Bill Andrews of Sierra Sciences is also testing a range of possible telomerase boosters.
The main reason why we should be taking anti-aging research serious now is because for the first time ever, there's been proof of concept, proof of principle experiments that have been done where they've never existed before, but where we've actually done things like make human cells in a petri dish immortal. We're way beyond the hope now because we actually have a target, preventing the telomere shortening.
But while his company searches for a better drug, he's been taking TA65.
I've seen my running improve, I've seen my vision improve. A year after I started taking TA65, I had to get a new prescription of glasses because my eyes got younger. Now, another thing is I used to have age spots on my hands. They've just suddenly disappeared. I don't remember when. So I don't know if that's TA65 or something else, but they're gone.
For some, this research is important. It's pushing the boundaries. But so far, TA65 has not been verified by the scientific community.
Well, they're a sort of a nutraceutical kind of a company that doesn't have to go through any kind of an FDA approval or any oversight of the science at all. And they have yet to publish anything that shows that their compound does anything to telomeres.
There's no scientific data, none at all, that says this in any human study has any effects. It's not an unreasonable idea. It's just that there isn't anything out there right now, and people are interested in that kind of thing, but there's nothing scientifically validated at this point.
I just was afraid that I'd wake up 20 years from now and nobody was doing this research. Nobody was just trying to find a drug that turns on telomerase to ask the question, does it cure aging? Does it stop the aging process?
There are those who believe it's only a matter of time before science discovers a way to activate telomerase in people. And we'd all want a little of that boost juice, wouldn't we? Perhaps not, for there is a sting in this tale. The very same enzyme that keeps cells young can kill.
So time, which was the cause of all this trouble, went on.
As in many a tale of immortality, the price of seeking endless youth is often death. And now, as the mechanism of cellular aging becomes clear, a paradox is revealed. The same enzyme that fuels life fuels cancer. Cancer cells are healthy cells gone terribly wrong. And a key to their deadly success is the enzyme telomerase. When a cell's DNA caps become too short, the cell usually stops reproducing and eventually dies. But occasionally, instead of dying, the cell undergoes a number of changes that can make it cancerous. And one of these changes is turning on telomerase. The telomerase enzyme provides the fuel that allows cancer cells to replicate endlessly. So cancer cells like these are the true immortals. And 90% of cancer cells have hyperactive levels of telomerase.
There's really two facets to it. It's sort of like Jekyll and Hyde. Dr. Jekyll was, the good, benevolent face. And so this is telomerase in normal cells. Now, in a very different setting, which is cancer cells, telomerase is very hyperactive. It's revved up. And in that setting of cancer cells, telomerase is actually very bad news because it gives the cancer cells permission to keep on multiplying. It's as though you've given the psychopath a weapon, which in the hands of a normal, social citizen like a normal cell is perfectly responsibly used, telomerase. But in the hands of the psychopath, the cancer cell, telomerase is bad news because it gives it extra power to keep on being cancerous.
In cancer, telomerase is no longer the hero, it's the villain. So this time, instead of boosting it, the challenge is to knock it down. In San Francisco, at Liz Blackburn's lab, they've shown this idea can work.
These ones, though, are always being covered by the 10 or 11, basically.
They inserted faulty telomerase genes into cancer cells, and the cancer cells hated it.
And within a week or so, the cells are really very miserable. And when we see miserable cancer cells that have, hated their lives so much they've committed suicide, we like this.
Across the world, there are high hopes as many researchers target telomerase. And given some cancer cells have found alternative ways of producing telomeres, the focus is expanding. For understanding how cancer becomes immortal is one of the most significant new approaches to detecting it and stopping it. So like a runaway car with failing brakes and endless fuel, cancer is a true immortal. But rob cancer of its vital fuel, and eventually it stops. Paradoxically, this key to cancer's deadly success is also the key to why our cells age. But why has nature evolved this double-edged sword?
The reason we age is likely as a mechanism to prevent cancer as we evolved into a longer-lived species from what we were in times past. And so the repression of telomerase, the robbing of immortality from cells in our body, the giving of cells of sort of like a finite fuel supply, helped prevent cancer and helped us live as long as we do. So we think of a yin and a yang. There's cancer and aging. And by extending telomeres and extending lifespan, we're probably increasing the risk of cancer. But as we've thought very carefully about that yin and yang, we think there's like a tightrope you could walk, a balance where we could find a way to extend human lifespan without causing human cancer, It's that yin and yang, that balance between aging and cancer, with, I think, science and medicine will be dealing with in the coming decades.
That balance is critical, for we all rely on low levels of this same fuel to protect our normal cells. Just how important this is can be seen in people whose telomerase system is malfunctioning, like Ray Newsom. At 16, Ray has a rare genetic disease called DKC, dyskeratosis congenita. It's causing him to age prematurely. He has bone marrow failure, lung and heart disease. His major organs resemble those of a 90-year-old.
He can't do the things that we're supposed to do in life. When it's a chore to walk from the kitchen to the living room, and it's exhausting for him, that's not life. And that's how it is for him. So every day is a wait. Every day you wake up and you're wondering if you're walking down the hallway, is he gonna be there or is he gonna be gone?
Dr. Mary Armanios is a medical doctor and researcher. She's been working with Ray and others seeking clues.
It's a classic premature aging syndrome, but it doesn't necessarily appear on the face, but it appears in internal organs, and it leads to a life-threatening condition. When we looked at the sequence, the DNA sequence of his telomerase genes, we were able to find a mutation that makes his telomerase defective. So, in effect, instead of having two healthy genes from his parents, he has only one healthy copy of telomerase. So telomerase dose is so tightly regulated that if we lose just a little bit, it's catastrophic for the integrity of certain organs, and especially the bone marrow and the lung. So his bone marrow could be compared to the bone marrow of someone who's 80 or 100 in terms of telomere potential.
Mary discovered some patients with a common lung disease also had similar genetic defects.
In individuals who have telomerase defects, they have an increased likelihood of getting idiopathic pulmonary fibrosis. And this kind of opens a new window, allowing us to appreciate that defects in the telomere cause diseases that have a much broader spectrum than we ever anticipated.
Shorter telomeres are now being linked to many common diseases of aging. Distinct patterns are appearing.
The shorter they are, the more likely the person is to have a risk of cardiovascular disease or risk of diabetes or risk even, it's now emerging, perhaps of cancers. We really think this is something to take very seriously as potentially underlying why people get diseases.
20 years after Cal Harley first tested his family, telomere testing is becoming increasingly common.
We're going to do the follow-up to look at whether or not the rate of telomere change is different amongst us, or whether we have longer than average or shorter than average telomere lengths. Is anyone nervous? I bet Dad's a little nervous.
Across groups, telomeres are revealing important clues about susceptibility to disease. But for individual people, it's an evolving science.
Now, how predictive is it? Except for the very short telomeres, we don't know that yet, but we would love to start finding out what about over time and so forth. I think people have been sort of captivated by this idea of the telomere because there's something very intuitive about the idea that something running down over time, a candle burning down over time, there's some metaphoric aspect which I think people kind of see how this would connect with aging. And the fascinating thing is it's not connecting so much with the clock of aging as the processes that go on that can lead to diseases of aging. It's that part of aging that it seems to be connecting with.
It turns out Cal's family are in the normal range, although, as expected, their telomeres are shortening with age. But here's the good news. Our telomere length is not set in stone. It's malleable. And it seems there are ways we can all increase our telomere length right now. Amazingly, lobsters don't appear to age. When small young lobsters are compared to bigger long-lived adults, they show no difference in speed, strength, or virility. It seems accidents, sheer size, or predators kill lobsters, not time. When researchers went looking, they found high levels of the immortalizing enzyme telomerase. And this maintains the length of the telomeres. So how can we be more like a lobster? It seems how we live plays a crucial role.
That's it. All right. How your legs feel, Mom? They hurt?
Paulette Salt is 65. She juggles a full-time job with caring for her 100-year-old mother, Alison, who has Alzheimer's disease.
Okay. The hardest is that I can't communicate with her. I know she's in there somewhere, but because of her deafness and because of the dementia, she's sort of in another world. You know, when things go wrong, she's in pain or she wants something and she can't verbalize it, and I'm trying to figure it out. I get frustrated. Okay. And then I usually have to walk away because I don't want to lose my temper. It's not her fault.
She also shares her house with her disabled brother, Peter. Her life of chronic stress is taking its toll.
All right, I'll put your shoes on and we're gonna get ready to go. I tend to be very restless, very nervous. I catch colds easier. I'm more prone to headaches, and it usually comes right after I've had a frustrating day with her or both of them.
She's been taking part in a study looking at how stress, literally, gets under your skin. Psychologist Dr. Alyssa Rappel specializes in studies of chronic stress.
Hey!
Hi, Liz.
She teamed up with Liz Blackburn to see if stress could be measured inside a person's cells.
CD8, 28 minus. So I was really interested in whether we could look at how stress causes wear and tear at the cellular level in healthy people. Can you see the damage from chronic stress? And where is that? Is there a little counter in the body?
What Alyssa does is it's about the whole person, right? And it's about their whole life, and it's sort of very, I don't know what the word would be, macro or something like that. It's very integrative. And my whole science had been very, very much, I want to understand the tiny molecular mechanisms of things and how these little tiny molecular processes and machines inside cells work. So how does it all add up and sort of play out in the life story of an organism or a person?
Alyssa chose to study women who care for disabled children or a family member with dementia, people with high levels of ongoing, unavoidable, chronic stress.
Family caregivers are known to have tremendous burden of stress day in and day out, and they tend to not be able to take care of themselves very well. So there's a tremendous amount of depression and more of a suppressed immune system in caregivers. Caregivers who report a lot of stress actually tend to die earlier. So today's going to be just...
They were looking for a link between high stress and the wearing down of telomeres.
And how have your feelings about her condition changed?
The last time we talked, I think I was pretty much frustrated a good deal of the time with her.
In the early studies, when they compared telomeres from the most stressed women to the least stressed, they discovered something shocking. The stressed women had an additional 10 to 17 years of cellular aging.
The more years the women had been caregiving the shorter their telomeres and the lower their telomerase. So that is the dark side of caregiving, that even if you're coping well, we know it has a wear and tear effect.
They also tested healthy women who were not carers. And surprisingly, those who had high levels of perceived stress also had shorter telomeres.
We know that perceived stress matters regardless of your situation in life, and that's good news because that's something we can work on changing. But telomeres are a very early sign. They are like a canary in the coal mine. They are one of the markers of biological aging that we have a grip on.
So the crucial question is, can we undo the damage? A remarkable pilot study in men suggests yes.
Well, I always have been a type A from high school on. My career was a very big part of my life. I've been the CEO of several companies, mostly in the technology field. I was a driven kind of a personality. When I found out that I had prostate cancer, you know, it's the kind of thing that one reevaluates what life is about. And as a result of that, I began to take a look at how I was living my life.
So begin by bringing the awareness to the crown of the head. Draw the awareness through the scalp muscles.
Jack joined a study that was looking at men with low-risk prostate cancer.
As you inhale, imagine that you're inviting in whatever qualities you need.
Instead of surgery, this group chose to change their lifestyle. They took on focused relaxation, regular exercise, a low-fat diet, and a great deal of emotional support.
Through the whole trunk of the body.
And we found that after just 3 months, men who made these changes, that over 500 genes were favorably affected, in effect, turning on or upregulating the disease-preventing genes.
Dr. Dean Ornish led the pilot study in collaboration with Liz Blackburn.
We also looked at telomerase in the same group of men, and we found that after just 3 months, telomerase was increased by almost 30% in the men who made these changes.
Again, breathing into your possible future.
It looks like I aged 29% less during that 90-day period. And that changes nearly everything. And I now have a different expectation about how long I'll live than I did before. I want this kind of life, and it's nice that it's going to go on for longer than it would have.
Now, when you first found out you had prostate cancer, you were pretty depressed. And did you find that being able to do something about it was empowering in that way?
Tremendously. The support group also was a very important meeting.
But could higher telomerase be bad news for Jack's cancer?
So yes, there's a theoretical risk that increasing telomerase might be associated with increasing cancer because cancer cells produce increases telomerase. That's what keeps them alive. But we didn't find that in these patients because we found that when we actually looked at their prostate cancer or their gene expression, they got better.
I'm not willing to say the cancer's gone. They just can't find it anymore. All right, the last 3 biopsies were negative. I'm going to die of something else well before the prostate cancer catches up with me at this rate.
If this was a new drug, it would be a billion-dollar drug overnight. And yet these are things that you can do for free simply by changing your diet and lifestyle.
That's it.
Paulette has also had some good news.
Don't drag your feet, Mom.
The Carer study and other studies around the world found that exercise and a reduction in stress and negative thinking can change telomere length.
In up to 25% of people, telomeres are actually getting longer over the course of a year or 2. This was really an exciting finding for us because rather than just, the gloom and doom news of chronic stress, we now know that telomeres and stress track together. And so if stress is going down, telomeres are lengthening.
Before, it was more of a black box. We knew if you change your lifestyle, things got better. Your heart disease could improve. Your prostate cancer often improved, and so on. But we didn't know why. And now, for the first time, we're understanding at a genetic level that when you change your lifestyle, it changes your genes, it changes your telomerase. That's a powerful motivator for many people.
So if we can keep our telomeres from shortening, can this protect us from the diseases of old age? At 92, Dal Richards has no detectable signs of cancer, diabetes, lung or heart disease. He is one of the super seniors, a group of remarkably healthy Canadians aged 85 to 105.
I can't remember when I last missed a gig. I really can't. It must have been many years ago. And we play a lot of gigs, like counting my radio show, a couple of hundred a year. So I'm out there with my horn pretty often.
Geneticist Dr. Angie Brooks-Wilson was surprised at what their DNA testing revealed.
We found that the super seniors did not have an unusual telomere length. They didn't have the really long telomeres we suspected we would see, and neither did they have exceptionally short telomeres. They actually seemed to have quite an average telomere length for their age, and they tended not to vary relative to each other. So it suggested to us perhaps the super seniors actually have an optimal telomere length.
Optimal telomere length. Long enough to keep vital cells renewing and tracking with a longer, healthier life.
Getting ready to dance, getting ready to be swinging with Dal tonight.
So, as we glimpse the extraordinary power of the immortalizing enzyme, is human immortality really on the cards?
It sure works for cells grown in the laboratory. The question is, if you put it into cells in the body, would it immortalize you? And, there's certainly no guarantee that that would be the case. But it'll certainly keep some cells going for much longer.
So certainly from the standpoint of cellular divisions, telomerase could be considered an immortalizing enzyme. But that's not immortalizing in terms of the people. There are many other inputs into immortality.
In a way, I think it's unfortunate that the use, immortalization and immortality, has been applied to cells that can escape the aging process. It's hampered research. It's caused skepticism. The thoughts of some is that we're trying to play God. We're trying to usurp the role of religion in offering immortality to people, or trying to build it in the laboratory. By immortality, we mean cells that can replicate without limit. The immortalization of man, the transformation of Homo sapiens to Homo Immortalis, is the work of science fiction and novelists.
But this discovery, together with other insights into cellular aging and renewal, is poised to dramatically improve how we age.
Easter Sunday, in the year 1513, that Florida was discovered by Ponce de Leon, and thus ended his long, tedious search for the fountain of youth.
What feed? Give me a big glass.
We've never been able to make young cells of any kind to repair the human body until today. We now know how to take a cell from an aged human, take it back in time to the cells we were born from. Reset the clock of aging in the process and make any kind of cell of the human body, beating heart muscle, bone-forming cells, cells of the retina, every cell of the human body to repair the human body. Humanity now has in its hands the power and the technologies to do these things. It'll be fun and interesting to see in the coming years how that actually plays out and how it's applied into the treatment of age-related disease.
If we can delay aging and decay, that's a good thing, so that we can die young, as old as possible. In other words, biologically, we want to have a compression of morbidity, that instead of having this decline over time, that we can be vibrant and healthy until the last few weeks of our lives, and then maybe things decay. That, to me, is a goal worth striving for. But simply living longer in a debilitated state, who wants to do that?
In 2009, the discovery of the mechanism that keeps our cells young and fuels cancer was awarded the Nobel Prize for Medicine. Professors Elizabeth Blackburn, Carol Greider, and Jack Szostak shared the prize. It honored a journey that had started over 30 years earlier.
Well, I think curiosity, is the most important thing that can drive science. You're kind of opening up your mind to all the wonders of nature, and you're trying to say, how does this work? The story's not over yet. We're not at the end of the line, that's for sure.
Most of us hope to hold on to life and all it offers for as long as we can. Now a new picture is emerging of our power to influence how long we will live and how well.